Okay, when we create our ordinary least squares model, our regression equation is the equation of straight line. Just like with our ANOVA models, we made some assumptions and then said, oh, there is an effect or there isn't, right? About the factors involved. So really, I want to think of our linear regression model as that's the line we came up with. And if there's no correlated error in our relationship between X and Y, then there should just be some overall error term. Just like with our ANOVA, we had the A factors contributing some variation and the B factors contributing some variation. And then there was some interactions if we had replication in our two-factor ANOVA. And then there was this error term. I said we made some assumptions, but I didn't actually talk about what those assumptions are. And the assumption about this error term, there are three main ones. First is that it's normally distributed. Now, why is that something we want to assume? Why does knowing my error is normally distributed matter? It doesn't actually affect my degrees of freedom, but that's related to the idea. The degrees of freedom in here are the same as in my ANOVA calculation. It's going to be based on my population size, which is the number of samples, my number of XY pairs. And I should still be doing n minus 1. But it actually comes out of any sort of preferential behavior. If I have a normally distributed error, then it should be just as likely for me to have a little error under as it is to have a little error over, right? And so that should balance out in the long run. On the other hand, if all of my small measurements had high errors that made them bigger than they should be, and all of my big values had low error that made them lower than they should be, that'll change the way my line looks, won't it? That'll change the slope of my line. That'll tell me whether or not I actually have a correlation or not. My p-value, my confidence interval will change based on the errors being not normally distributed. There was a predilection for the error in one place or another. And then I'm assuming that this has constant variance. That whatever the variation of error is for small values of X, it's the same as the variation for large values of X. And third, the errors are independent. So it doesn't mean that larger values have larger errors or larger values have smaller errors. It means that I get the same kind of error regardless of where I am in the line. There's just one problem. I don't know what that number epsilon is. I don't know what the error is. So what I can do is I can actually look at how the line goes through my data to try and figure out what's going on here. And to do that, I'm going to look at the residuals. For every one of my X values, I have a Y value that goes with it. right? That's the Y value in the data you gave me. Let's assume that we are talking about one of the settings that we were talking about Wednesday or Monday. Home price versus square footage, right? Okay. You gave me the size of the house. I told you what the price was in the data that you provided me. Then I created a prediction. And that is based off my line. So I also have for each of these a new Y value. I need to indicate that this Y value is different somehow. I know. This will be the Y value that comes from my line. I'll give it a hat. This is the Y I get out of my line when I plug in that X value. They might not be the same. So it is perfectly reasonable for me to say, you gave me, for an X value of 1,000 square feet, you said that the price of that home was $57,000, but when I plug it into my linear equation, I actually get $55,000. The difference between those, that's my residual. So if the residual is positive, it means that the expected value, the predicted value from my line is a little lower than the actual dot. And if the residual is negative, it means that the dot is below the line. So if I create a scatter plot, grab the textbook and pull a scatter plot out for you. Here is our example about study time and exam grades. This is on page 470. We had the amount of time people studied and then their score on the exam. This is all of that by hand calculation that would need to be done to set up the regression. We didn't do any of this crap by hand. I stuffed it in Excel. I got out this equation. If I plug in 8 hours for Oscar, they actually got a score of 43, but I'm predicting they should get a higher score. So this is a residual that is negative. This is a residual that is positive. This person, I'm assuming this is Mary because they studied for 5 hours, got a score of 74, but I was predicting a score around 58. Make sense? So here's my question. Since I can't observe this directly, how does observing this set of residuals help me? It turns out there are some easy visual clues to determine whether or not my assumptions are valid. So let's think about this normal distribution. If I don't have enough data, then I would need to do a t-test to find my variation, right? I'd have to do an f-test to find how the variation behaved against one variation versus another. So this is where I start to run into my problems analyzing the variation. If it's not normally distributed, I can't use a t-test. Uh-oh. Okay, I used my t-test, I determined p-values for those, right? What p-value was I doing? I was creating a p-value for the slope and the intercept, right? When I look at that bottom line of the analysis that goes with my regression, I can see a p-value. Do I think there is a non-zero slope? If the slope is zero, then I can say I don't think these are correlated at all. The closer my slope is to zero, the less relationship I think there is. Okay, wait a minute. How can I get around this? What was my threshold that allowed me to say, well, in spite of not being normal, I think I can still get away with it? We had particular values that we could use. I had to have enough data, right? What was enough?
Are you talking about if the uh sample is effectively infinite, the end is effectively infinite?
That was our population being effectively infinite. That told me I took a small enough sample that I didn't have to worry about that finite population control thing.
Yeah.
Unfortunately, no, not in this case.
Uh-oh.
But that is something to be wary of, right? I need to make sure that my sample is representative enough. In small populations, I stand the chance of resampling, right? I could pick the same person twice. But if I have an effectively infinite population, that just basically goes through the floor and I don't have to worry about it. This is actually something different. I need to make sure that my sample is big. So I use little n, not capital. Capital N is for my population. So how do I know my sample is big enough? We actually had a threshold for this.
Like, 30?
That was my number. It was 30. If I have more than 30, I should be okay. So large enough means more than 30, or maybe just that 30. But I also need to know one other thing. I need to know that my number of outliers or extremely off the line values is small. N is large enough, and we have, I lost the phrase, no extreme outliers. Now, this is usually a very mild variation. Sorry, violation of normality. If I have extreme outliers, I might want to use a T instead of a Z. I might not be able to do the same test I normally do. How can I check? So now we get to the big question. How can I check this? All right. Let's pull up an example. Here is step 12, section 8 example, which talks about cockpit noise. At airspeed. So all of these aircraft are 727s. Sound levels measured in 7 different aircraft at first officer's left ear using a handheld video. For reference, 50 decibels is normal conversation, 75 is a vacuum cleaner, 85 is city traffic, 90 is a hairdryer, 110 is a chainsaw. I don't want to be standing next to a chainsaw without ear protection. For the record, standing at the end of a runway as a jet is taking off sees noises of 120 to 130 decibels. The loudest rock concert, they shut down the city, was measured at 128 to 135. It registered on the Richter scale. This is what happens when you get an entire football stadium arena to bounce in the middle of a Metallica show. So let's take a look at this plot and the ordinary least squares regression we get from here. So I'm going to do the same data analysis we've been doing this whole time. Regression, input Y range. There are the Y's. Oop. I got to finish with the X's. Here are the X's. Yes, I checked the labels. I want everything in a new workbook. Now, there's a whole bunch of stuff down here. Those checkboxes that I said ignore, let's not ignore them anymore. The 2 checkboxes to the left, immediately below where you can put the option for the output, those say residual and standardized residual. I'm going to check those 2. And when we generate this output, we're going to get a lot more information. Holy moly. Okay, so let's start up here at the top. Is there a relationship between airspeed and cockpit noise? Why not?
I know we. Yeah.
Again, why?
With R squared.
R squared or R, either one, right? Those top 2 numbers. R value is 0.94, the R squared is 0.89. Okay, R squared is my coefficient of, which tells me that 89% of the variability in noise is due to airspeed. Okay, that's a relationship. Most of the change in noise is due to my change in airspeed. I could go 2 other ways to answer this question. What other 2 numbers could I look at on this screen and have myself answer yes or no?
F and significance F.
That absolutely is one of those numbers that helps. I need the significance F more than F itself because I don't have a critical value for F here. So the significance of F will help me here. That is 1.59 times 10 to the negative 30th. There are 29 zeros in front of that. That is really, really, really small. If my alpha is 0.05, that's way smaller. The other number I can look at is in the next block down, where I have the airspeed coefficient and its p-value, which is that same p-value, 1.59 times 10 to the negative 30th. Yes, this correlation has a strong p-value. But please notice, the slope itself is fairly small. There isn't a lot of increase in noise per increase in airspeed in terms of the units they've given me. Our units were, let me go back and look. Airspeed is in nautical miles per hour, knots in airspeed. So to go from 250 to 251 miles an hour, my sound increased, but only by 0.07 decibels. So I really have to jump up quite a bit in speed to notice a decibel increase. Okay, physics class might have been a long time ago. Anybody remember what decibels measures? Well, it gives me how loud something is, right? But it's a logarithmic scale. Every time you go up 1 bell, decibel means tenth. So every time you go up 10 points, you double the intensity of the noise. So going from 60 to 70 isn't an increase of 10, it's an increase of 100% of the noise. All right, so going from 50 to 51, 250 to 251, in airspeed caused me to increase 0.07 decibels. It's not a lot of increase in noise, but it was a very small increase in speed. Down here, this is where now I can start looking at the meat of this setup. Format, autofit. Here we go. So that first thing, airspeed of 250. My model tells me I should get a noise level of 83.36. But I actually got a noise level of 83. So I take my predicted value and subtract it from the actual value. There's a negative residual. The line is above the dot. But now I can look at all of those residuals. Standard residual. Well, if I look back up a little higher, I will notice there is a standard error up here. That standard error, that's what I'm dividing by to create the standardized residuals. Just like when we had standardized z-scores, right? That's how we got a z-score. We took the value minus the predicted value and divided by my standard deviation. I'm doing the same thing here. I'm taking the actual residual and dividing by my standard error to get this standardized residual. So I'm going to treat that last column there like z-scores. What does it mean to be an outlier?
It's like an unusually high, like outside the normal range, like way out.
Right. But if I'm treating it like z-scores,
Like more than 3 or less than -3, like maybe Z is 4.
I need to be outside of 3 to -3. So I can look through this list. And I can simply say, hey, are any of these huge? Matter of fact, here's what I'm going to do. I'm going to highlight this column. And I'm going to go up there where it says conditional formatting. You did this in the data class when we talked about making heat maps. Let's make a conditional format. And I'm going to format anything in this cell. I'm going to highlight it. If it is greater than 3, we'll color it red. Then I'm going to do it again. Highlight less than -3. And now I just have to look for color. Nothing lit up. None of these are officially outliers. I could check for unusual. What does it mean for a data value to be unusual?
Be between -2, -3, or 2 to 3.
Between 2 and 3, and absolutely same deal. I could highlight for those ranges. I do see a couple. I see at least one that's 2 point something. There it is, 2.09. I haven't highlighted it yet, but there's the number. I thought I saw another one. Yep, there's another one right here. So if I went through that same process, conditional formatting, highlight greater than 2, but this time let's change that to be yellow. See how those lit up? I can do the same thing for -2s. But there aren't any negative residuals. There are only those 2 positive unusuals, not outliers. I could even make a histogram, right? With ranges of 1, and then I'd be able to see if there were anything weird going on here. I don't have to do this manually. I wanted to know if these were normally distributed, right? So I could actually take my prediction of what a normally distributed error should look like based on that standard error value up here. That standard error value is 1.29, whatever up there. I could say, oh, well then 64% of the data 68% should be between -1 and 1 standard deviation. 95% should be between -2 and 2. 99.7. So let's draw a line based on these values, and then we'll plot these actual values. Again, that comes from doing the regression. I'm going to check something else. This quartile plot, it's not up there as quartile. It's up there as normal probability plot down here. That'll actually give me a straight line of what would be a normal distribution, and then it'll plot my errors around them. I'm going to turn off the residuals and the standard error this time because we already did those. Here is my normal probability plot. It's not a perfect straight line, is it? But it is going the right way, isn't it? As we go from 0 to 120 to 100 in our percentiles, we're going up. It's not got to be a perfectly straight line, but if I laid a ruler across that, I wouldn't have too many things too far away, would I? That's the benefit here. This isn't straightforward, but if I compare this slope to a slope of 1, that looks right. So I'm happy about it. I would really only worry if I see major outliers, because that was my claim in the comment I made earlier, is that I need to have enough data values and I need not have huge outliers. Question? Here, by the way, is the histograms of our standardized residuals. You'll notice I have a couple up in the 2 to 3 range. I don't have anything above 2.5, I don't have anything below -1, -2. I don't have outliers here. Questions? Okay. That takes care of my first assumption. That's how I can check for normally distributed errors. The next thing I want to talk about is constant variance. So what would my errors look like if the variance depended on what X value we were at? A non-constant variance means that as I change from one X value to another, my variation gets bigger or smaller. Now, I've put some things in quotes here because really I'm not talking about the errors, I'm talking about the residuals. And I'm not talking about them being exactly the same, just mostly the same. We can have a little bit of variation. We were just talking about normal distribution. So I can have some variation in the residuals. I just don't want them to be hugely different. And I don't want them to be different in terms of the x's. My airspeed. My airspeed went from some minimum to some maximum. I actually don't know what the minimum and maximum are at the moment, off the top of my head. Looks like minimum airspeed is around 230, maximum airspeed is around 420. So I've got numbers between 230 and 420. So I could look at the residuals and I could plot them in a scatter plot. And when I do that, I'm getting a picture goes from 230 to 420 on the x, and has these y values that are between, well, we can even use the standardized residuals, negative 2 and 2.5, right? And now I can ask the question, what does this scatter plot look like? The scatter plot for our data set that I was just looking at is here on page 488. So these are the residuals based on the airspeed. As I go from left to right, I'm getting faster. But this is my predicted error versus my actual value, right? Predicted value versus actual value. If there was a trend where higher airspeed caused more variation and lower airspeed caused less, or vice versa, lower airspeed caused more variation and higher airspeed caused less, then I would expect the pictures to look different. Here are three different made-up scatter plots. They're not related to our problem at all. But notice the trend as we go from left to right here. This leftmost picture, as I go from left to right, it's spread out evenly. But in this middle picture, as I go from left to right, the variation gets bigger. And the third one, as I go from left to right, the variation is getting smaller. So these two tell me something's going on. I can call it a fan out or a fan in pattern. The formal term for this, I will never ever use again. When it's the same all the way across, it's homoscedastic. And when it's different, it's heteroscedastic. I hate that word. But that is the formal term. Here, something is happening. There is a relationship between the X value and the error I get. That means it's not constant across the setup. So this is the best way to check. Now, I said this was the picture for our setup. But I actually made that picture in Excel. There. I took our X values and our residuals, plotted them against each other. That's our plot. From -3 to 3, 200, 450, I get all the data. Do you see a growth as we go from left to right and how far these dots are from the center? Or a collapse as they get closer to the center? Doesn't look like it to me. And there are only 61 dots here. But I don't see that growing pattern or that falling pattern because I've got just as much variation here at the left edge as I do at the right edge. Now, I think I'm really going to put a lot of weight on the fact that on the bottom here, it looks like it's growing. But that one over there on the left at the top means it's kind of more level across the top. And that level tells me I don't have good enough reason to suspect that there's a relationship here. This variation looks to be good enough. Okay, so that's my method for checking whether or not I have constant variance. What was my third one? Aha. So this would be not only does it move in one direction or another, but it actually depends on the individual X value in a pattern. This shows up more often in time series data than it does in cross-sectional data. So I'm going to pull an example out of my ear or some other orifice. We talked about correlation between ice cream sales and drownings, but let's just talk about ice cream sales for a moment. Do you see why it would be reasonable for me to say that there's more variability for ice cream sales in certain types of weather?
Yes.
If it's hot, a lot of people are going to buy ice cream. If it's cold, you may have some people who absolutely love their ice cream and aren't going to stop buying it. So I could say by time, I would expect a rise or fall based on the season. As a time series data, that means that the variability is going to adjust as I go from spot to spot. This is called autocorrelation. Autocorrelation can be done a lot of different ways. The easiest compares one back. So compare yesterday with today. Compare today with tomorrow. Compare Saturday with Sunday. Right? Just move one data point back and forth. This is called first order autocorrelation. If there's a lot of data that is similar, then I would expect those changes to be small, wouldn't you? If the data is fairly similar, I would expect we're not going to change sign and have something jump from above my equation to below my equation to above to below to above to below. So we look at the way the sign changes. If I see a lot of sign changes, that's unusual. Means the data is flipping back and forth across my line a lot. Here, I see a bunch that are above, a bunch that are below, back and forth very few times. So here are two sets of 50 observations. Here there were only 11 changes in sign. Here there were 36. This is more unusual than this, a lot of flipping back and forth. So when I see more changes, we're going to call that negative autocorrelation. If I see few of them, we're going to call that positive autocorrelation. Positive autocorrelation and negative autocorrelation both can lead to narrower confidence intervals. They can decrease the size of my standard error. Again, in our Excel example, here are all of the residuals just plotted one after the other.
Does does it only become negative autocorrelation if there's a lot of changes over the zero?
Yes. The wiggling back and forth isn't a problem. It's the flipping back and forth across zero. The change in sign is what gives this positive or negative autocorrelation. This is more common, again, in time series because I see cyclical patterns, right? In a positive autocorrelation, it's ice cream season, it's less ice cream season. It's ice cream season, it's less ice cream season. Back and forth, right? But here's my result. I don't see very many sign changes. I see, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19. Oh, 42. Out of 61, it's not a lot. It's not trivial, but it's not a lot. I'd say this data is more positively autocorrelated than less. Again, this is not the best way to look at this, but it is the easiest. There are other autocorrelative methods that we will cover next semester in the quantitative business decision making course, 451. There's a moving average idea, there's additional methods of regression, and there is higher order autocorrelation that we can look at. Question. The one thing I have not shown you for this data is the actual plot. Nope. I didn't make it apparently. So let's plot these against each other. Insert scatter plot. Ooh, that's wrong. Let's go that way. Okay, so this is our scatter plot. Here is my trend line. Yes? If I have outliers in my standardized residuals, I would expect one of those dots or more of those dots to be really far away from that line. I can clearly see where I think those two big residuals were. We had two that were unusual. They weren't outliers, but they were unusual. I think this is one of them right here. That looks like it's the furthest away from my line on this side, on the left. I think there's another one up here that's just as far away on the right. We could go back and actually find which two had the biggest residuals. We had those numbers. They were highlighted yellow. When I have numbers that are sufficiently far away from my line that they look like they affected the whole line, I tend to call those values of high leverage. And I will be 100% honest with you. There is a formal definition of what it means to have high leverage in terms of computing a value. I've never used this computation. Here's a formula for a leverage value. I can't do this in Excel except manually, so I don't. I mean, I can do it for our one example, but oh, it's going to take me working this whole thing out by hand. But look at the picture. We've got this really far data value away from the main body, don't we? If I moved that one, that would change this whole line, wouldn't it? If I moved that one, because they're far away from the average X value, not Y value, but X value. So high leverage, these are called influential observations or influential data points. We could actually omit the outliers, and we did that before when we did our trimmed means, right? So we can say, this one is so influential to the rest of our data, I don't want to use it. But if I take one off the top, I have to take one off the bottom to match those two up. I do not expect you to be doing these calculations manually. I don't really expect you to be doing leverage calculations at all by hand, unless we've got the software to do it. I'm not going to touch it. I did put that example on our Canvas page. You should look through it. Our homework for this chapter is due Monday. Our exam is Thursday at 8 in the morning. Here. You are permitted the formula sheets you've used before and a new one. Make sure the ones from before have my initials on them. If you didn't use one for one of those and you want to write a new one, that's fine. Handwritten, one side of one page. I will see you all on Monday when this homework is due. Have a wonderful weekend. Bring questions. Yes, sir.
So